We want to continue this idea of being able to predict relative strengths of acids based on what's in the molecule, but now we want to focus in on oxyacids. So again, when we are predicting acid strength, we can use one or both of our options of basically, is the acid strong because the HA bond is weak, right? Is it relatively easy to donate H pluses? Or is the acid strong because the conjugate base is really weak, right? Is this molecule bad at taking on H pluses, meaning that it can't really do the reverse reaction very well, meaning the equilibrium will lie on the product side. So either of those can be used to analyze and understand these acidity trends. So an oxyacid is anything where you have hydrogen bonded to oxygen, which is bonded to something else, which we'll call E as kind of our generic rest of the acid molecule. So here's kind of a general schematic of what they look like up here. You can generally make these with any sort of other atom being E. So for example, we can have the halogens, right? Iodine, bromine, and chlorine. And basically the structure of the molecule will always be that the acidic hydrogen is bonded to oxygen, that is then bonded to this other thing, chlorine, bromine, iodine, whatever it is in this case, that you would have that other kind of atom there. But the important thing is because it's an oxyacid, the hydrogens are going to be bonded to oxygen. So that does kind of clean up a lot of the variation. The variation is all going to be in the rest of the molecule. And as a result, we can get some nice trends, some nice relative acidities, and make predictions for this family of acids. So if I have acids, I can look at the conjugate bases. If I want to predict strength, I need to use both of those representations. So for an oxyacid, the more electronegative the E atom is, leads to a stronger acid. So chlorine here is at the top of the halogens, or near the top of the halogens. So that means it has a higher electronegativity than bromine, which has a higher electronegativity than iodine. And we therefore predict that that's the same order that we find for acid strength. So as we go up the period, we get stronger acids. And the reason for this is actually all in the base description. That basically the reason why HOCl is a stronger acid is because OCl minus is a weaker base. And the reason is because you have that more electronegative atom. We know that it's this HO bond that breaks. And so the negative charge is localized onto the oxygen atom. That's really where it kind of goes because that bond went from being a bond to being a lone pair on the oxygen atom. And so because the chlorine is electronegative, what ends up happening is some of that electron charge gets pulled over towards the chlorine, and it makes that kind of charge, that extra negative charge, is less concentrated on the oxygen atom. We know we've seen before, like in the case of like ammonia, where we have nitrogen with lone pairs. Those lone pairs are what make it a base. And so, if those lone pairs are kind of a little less concentrated, a little more pulled over towards the chlorine, a little more shared across the whole molecule, it's going to make it a worse base. Whereas in the case of like iodine, because iodine is less electronegative, this is really just like charge lone pair sitting on the oxygen, very localized, very attractive to H pluses. It's going to be a better base. And so because that's a better base, it's going to be hard for this molecule to say react with water and donate those hydrogens. So it would be a weaker acid. Now I want to look at oxyacids where there's additional oxygens that are bonded onto your base atom or your E atom. So we could look at, for example, I have all the chlorine situations where in all of these cases I have my chlorine atoms that are bonded to the OH, that's an acid, but then there's additional oxygens bonded onto the chlorine atom. And the more oxygens that are bonded onto that central chlorine atom means the stronger the acid is. So in this case, as I go up from either, I can see that I have 0 acids, I have 1 acid, or oxygen, sorry, I have 2 oxygens, and then finally I have 3 oxygens. That as those number of oxygens increases, I would get a stronger acid. So I need more and more oxygens, and you can just kind of relate acid strength to the number of oxygens that are in the molecule that are attached to that base atom, the chlorine in this case. And understanding this strength is, again, we need to turn to the conjugate base. What is the conjugate base, and then how is its strength kind of dependent? And we can see that the base strength is opposite for the acid strength, and it's the same kind of idea about electronegativity. We know that chlorine is relatively electronegative, so it's pulling electrons. These, say, extra electrons are pulled over towards the chlorine, and then what ends up happening is if you add some extra oxygens, they can also pull some of that electrons. They can also pull some of that negative charge, right? So they can pull some of that negative charge. More oxygens means you're pulling that electrons, that electron charge away. It's all about kind of delocalizing and pulling away that negative charge. Conversely, very strong bases have highly localized negative charge, right? It is on one atom. There is nowhere for it to go. In this case, we have all this kind of bleeding out, kind of sharing of the negative charge, leading to these things being really weak bases. There's so much electronegativity here that they're just kind of all pulling the electrons every which way off of that initial oxygen that was bonded to the hydrogen. Beyond electronegativity, we can also use resonance to explain what's going on. We know in the case of like ClO minus, there's only one resonance structure. But when we have something like ClO4, we can see that we have a choice. We have 4 oxygens that are bonded onto the chlorine. 3 of them are double bonds and 1 is a single bond. So there's a question as to where does the single bond go? And we know that in resonance, there is this actual sharing that occurs, that it's really a mix of all 4 oxygens containing that negative charge. So again, this is a way to kind of spread that negative charge, kind of spread it around where it goes. And you can see really, and again, these graphs, the green means that the oxygen, there's not really a bunch of extra or too little electrons. So in ClO, there's a lot of negative charge that's still on that oxygen. It is being pulled towards the chlorine, as we would expect, right? There's green over on the far end, but it is being pulled towards the chlorine, so it is kind of blurred a little bit, but there still is red coloration in there. If we go all the way down to ClO4, this is basically just green, right? Because it's just like an equal, very blurred out extra electron charge. There's no real area that's very electron rich or electron poor. Everything is just kind of equal. And so what that means is you don't have anywhere that you could say form a unique bond. That's what makes this not even a base, right? This is the conjugate of a strong acid. This thing is not going to accept electrons at all, whereas ClO minus is a pretty decent weak base, pretty high up there as far as weak base strength goes, because there is some negative charge, right? That electron-rich area in the red there, it wants to form bonds with some H pluses. We can use this idea of resonance to kind of explain other trends that we see. For example, ethanol is not an acid, whereas acetic acid is a weak acid. So acetic acid, CH3COOH. So we know that that is an organic acid. And this whole shape over here, or this whole pattern, is associated with organic acids. Organic acids always have that. Ethanol also has this O bonded to hydrogen, just like we see in the acetic acid molecule. But ethanol does not behave as an acid in water. Basically, that OH bond does not break. You don't produce H plus when you dissolve ethanol in water. And so if we want to think about why is that, we can look again at the conjugates. And so the conjugate bases here of what would happen if these things did behave as acids. Well, in the case of ethanol, you lead to putting this negative charge, boom, just right on the oxygen. It's bonded to carbon, which is a relatively low electronegativity, right? It's not like a chlorine or something that can help kind of pull away that charge. Instead, there is just a bunch of extra charge hanging out on this oxygen, very like just an extra lone pair that is a very, very strong base. That's very attractive to H pluses, really would aggressively react with any hydrogens that it could find. If we instead look at acetate, the conjugate for acetic acid, we can see that there is now an extra oxygen, which helps, right? The carbon, so the first rule, this idea of the oxyacids, you have the carbon is bonded to another oxygen. So that's kind of pulling away some of that. So just based off that idea, extra oxygens help strengthen your acids. Additionally, not only does that extra oxygen serve to help as an electronegative, but it can also be as a resonance stabilizer, so that you do have the potential to have a single bond. The extra electrons can be on this oxygen or on the first oxygen. Again, that helps to delocalize or kind of share where those extra electrons are between the oxygens, leading to this being a weaker base. Now, this is still because, again, we said the carbon's not really pulling a lot of work, not doing a lot of work to help stabilize. So this isn't a strong base, brain stretch the imagination, but it is a weak base relative to this molecule, which is extremely strong base, right? That is so strong. That's taking stuff off water, very aggressively strong base, going to take as many electrons as it possibly can. Participation 1017, question 3. For each pair of compounds, state which is the stronger acid. Give a brief explanation. A, H2O or H2S, B, HBRO3 or HBRO, and C, HF or HClO. This is the third question on participation 1017 due Friday, October 17th at 11:59 p.m. over on Blackboard. Link to the assignment is right below the links to these videos. Again, for each pair of compounds, state which is the stronger acid, give a brief explanation. H2O or H2S, HBRO3 or HBRO, and HF or HClO. That's it for chapter 14. It was a long one. So all the way back at like predicting neutralization products, that's where we started. Then into kind of ending with kind of return to acidity, kind of some looking at the more molecular side of the acidity, and a long time looking at equilibrium of weak acids and weak bases, all that kind of stuff. So there's a lot here that we want to keep track of. That's gonna do it. Participation 1017 had 3 questions. You want to find those questions, get them answered, get those answers submitted over on Blackboard by Friday night. You just got the week 8 homework due Saturday, and the acid dissociation constants post-lab due Sunday. Otherwise, it's going to do it for me. We got the participation questions that go live Friday night, the answers to the participation that go live Friday night. This is it for material on next week's test. If you want to meet before the test, anything like that, please don't hesitate to reach out. There's the review in the exam 2 folder. Get 3 points on your test score. Otherwise, that is going to do it for me. Have a good weekend. See you next week. Bye-bye.